Receptor exposure is exactly what it sounds like. This describes the amount of radiation striking the image receptor. For example, when a large number of X-ray photons pass through the patient and reach the receptor, that results in a higher receptor exposure. But when only a few X-ray photons reach the image receptor, that results in a lower receptor exposure. So why does receptor exposure matter? The quantity of photons striking the image receptor can have a significant effect on image quality. These 4 images were exposed to different levels of radiation, that is, different receptor exposures. Notice that extremely low receptor exposure creates an artifact called quantum mottle. This is a patchy or blotchy appearance that occurs when too few photons strike the receptor. This is also called quantum noise. With quantum mottle, there isn't enough image information to create a clear image of the anatomy, and that results in the patchy appearance. This is an unacceptable image that would need to be repeated with a higher receptor exposure. Also notice that extremely high receptor exposure creates an artifact called saturation. This is a loss of soft tissue contrast that occurs when the image receptor has received more radiation than it can process. This is also called burnout. In this example, the lung markings are not visible because of severe overexposure, called saturation. The anatomic information is gone. This is an unacceptable image that would need to be repeated with a lower receptor exposure. Both of these artifacts might cover important pathologies on the radiograph. It's kind of like baking cookies. The cooking time and cooking temperature doesn't have to be exactly right, but it does have to be close. Baking the cookies too cool or taking them out too soon results in doughy cookies that nobody wants to eat. The cookies never got enough heat to cook correctly. That's kind of like quantum mottle. Baking cookies too hot or too long results in burnt cookies, and that's kind of like saturation. So what affects receptor exposure? What affects the amount of radiation striking the image receptor? All 4 prime exposure factors, including the milliamperage, that's the MA, as well as exposure time, kilovoltage peak, and the source to image distance. Receptor exposure is also significantly influenced by automatic exposure control, that's AEC, as well as grids, filtration, collimation, the anode heel effect, and various other patient factors. An X-ray operator must consider each of these variables to ensure the receptor receives just the right amount of radiation to create a diagnostic image free from exposure artifacts. Let's look at how changing mass changes the receptor exposure and potentially changes the image quality. Increasing mass increases the number of photons created by the X-ray tube, which in turn increases the number of photons striking the image receptor. The relationship is proportional. If the mass increases by a factor of 2, the receptor exposure also increases by a factor of 2. Receptor exposure is affected by anything that changes the total number of photons reaching the image receptor, which is why kVp also has a huge influence on receptor exposure. Just like mass, increasing kVp increases the number of photons created by the X-ray tube, which in turn increases the number of photons striking the image receptor. But kVp affects receptor exposure in another way too. Increasing kVp also increases the energy of photons, and therefore the penetrating ability of the X-ray beam. A higher kVp means more photons in the beam, and a higher percentage of photons will penetrate through the patient to the receptor. So increasing kVp increases the photon energy, or quality, which then increases the receptor exposure, because a higher percentage of photons are penetrating through the patient. Because of the compound effect of kVp, the relationship between kVp and receptor exposure is more complex. It generally follows the 15% rule, which says increasing kVp by 15% will double the receptor exposure. Let's look at how changing the exposure technique and changing the receptor exposure changes the image quality. This series of images was created by changing the mass. You can see that one mass was too low. This resulted in inadequate receptor exposure in quantum model. You can also see that 100 mass was too high. This resulted in overexposure and saturation. The images acquired with 10 mass and 20 mass both have acceptable image quality. They look exactly the same, even though the image acquired at 20 mass has double the receptor exposure. This helps make an important point. You cannot judge the appropriateness of the exposure technique by the image quality alone. In this example, 20 mass was too high, since the same image quality could have been achieved at 10 mass. For all images, even if there's no artifact or errors on the image itself, there is a way to measure the exposure received by the receptor during processing. Each radiograph is assigned a number called the exposure indicator. An exposure indicator is a number that tells the operator how much radiation reached the receptor. If the exposure indicator is outside of the acceptable range, this might mean that something about the exposure should have been changed. Unfortunately for us, each vendor uses its own exposure indicator system. Fuji uses the S number or sensitivity scale to indicate the exposure. Carestream uses the exposure index values, and AGFA uses the log median value. All of these number systems are really very different. Fortunately, all vendors also use a universal exposure indicator called the deviation index, or DI. The deviation index describes the difference, or deviation, between the ideal receptor exposure and the actual receptor exposure. The deviation index scale ranges from 3 to -3. A DI of 0 indicates the receptor exposure was exactly on target. A DI of 3 indicates the receptor exposure was 100% too high. A DI of 2 indicates the receptor exposure was 58% too high. A DI of 1 indicates the receptor exposure was 26% too high. A DI of -1 indicates the receptor exposure was 21% too low. A DI of -2 indicates the receptor exposure was 37% too low. And a DI of -3 indicates the receptor exposure was 50% too low. These values do not measure image quality. There may be obvious artifacts, or there may not. These simply describe the accuracy of the operator's technique in producing the desired receptor exposure. The X-ray operator should review the exposure indicator or deviation index after every exposure so they know how they might adjust their technique in the future. For example, here's a scenario. A radiograph of the abdomen demonstrates optimal image quality and a deviation index of -1. What actions, if any, should be taken by the operator? The correct answer is D. The operator does not need to repeat the exposure. It's ready to be sent for interpretation. A DI of -1 isn't perfect. It indicates the receptor was underexposed by 21%. But if the image quality is good, there's no reason to repeat the exposure. Here's another scenario. A radiograph of the chest demonstrates saturation artifact and a deviation index of 3. What actions, if any, should be taken by the operator? In this question, the correct answer is B. The operator must repeat the exposure. The DI indicates the receptor was overexposed by at least 100%, and there is saturation artifact on the image. This means there are areas of soft tissue that are completely burned out and no anatomic information is visible. This problem must be corrected. So, to summarize everything in this lesson, receptor exposure describes the amount of radiation striking the image receptor. Correct receptor exposure is important to avoid image artifacts like quantum model and saturation. Quantum model is caused by severe underexposure, and saturation is caused by severe overexposure. Finally, receptor exposure is quantified by evaluating the exposure indicator or deviation index.